All right, welcome. So now we're talking about temperature. What is temperature? It's the average kinetic energy of particles. So it's measured in either degrees Celsius or Kelvin. Note that Kelvin, there is no degrees. And this formula is found on reference table T. It's pretty straightforward. So for example, if we had 400 Kelvin and we wanted degrees Celsius, I would put 400 into here, and I just solve it. So 400 minus 273. So I'll even show that. See what I did? So that's how you get 127. Now the other way, you've got 400 plus 273 is going to give you 673. And then 100 Kelvin, 100 equals degrees Celsius plus 273. Subtract 273 from both sides. Minus 173. Those are super easy Regents questions. I hope we always get those right. But temperature is different than heat. Heat is different. Heat depends on mass. Heat's measured in joules or calories. All right. Which of the sample have a greater average kinetic energy? Remember, average kinetic energy equals temperature. So they're related fields. All right, we have 50 milliliters of coffee and 50 milliliters of milk, same amount, but at different temperatures. So which has the greater average kinetic energy? Whoever's at the greater temperature, which would be the coffee. In this one, we have 100 grams of solid H2O, which would be ice, and we have 350 grams of liquid H2O, which would be water, at 0 degrees. So note that we have different masses, but if we're at the same temperature, they're going to be the same average kinetic energy. So don't get tricked. All right, how does heat flow? I know that if I put my finger in a candle, it's going to hurt because heat is flowing from that hot candle to my hand. So we go from areas of high concentration, which is warm, to cool. So here we have an ice cube melting. Let's say it's on a table or something. There's going to be heat coming from the table. There's going to be heat coming from the air. And so because the heat is going into that ice, it's going to melt. And heat's going to flow until both temperatures are the same. It's not going to be like an even, like middle, but it's going to be somewhere in between. Okay, now we have two terms having to do with heat either going in or going out. Endo is heat coming in. Heat is being absorbed. So think of me absorbing all the heat. I'm sucking it in. So if I absorb all the heat, you're not going to have as much and you're going to feel colder. So as the reaction sucks in the heat, the surroundings get colder. Here's an example. So we've got a beaker of water. It's at 10 degrees Celsius. I put in a green solute, something, and I dissolve it. So it's evenly distributed, homogeneous. The temperature went down of the water. So now if the temperature of the water went down, it's because the dissolving process absorbed it. So this happens in an air conditioner, where the air conditioner will take in the heat from the air and spit out colder air, or just something as simple as an ice pack. You put an ice pack on your body. Why does the ice melt? Because the heat is going from your body into the ice and thus melting it. And what does your arm feel? It feels colder. The opposite of endothermic is exothermic. Exo, think of exit. Heat is giving off, is being given off. So if heat is given off from the reaction, you're going to feel warmer because it's been given off. So here we have our beakers again. I start with 15 degrees Celsius, then I dissolve a purple solute, and oh my gosh, now the temperature has increased. So dissolving that salt or whatever has given off heat. We call it exothermic. Obviously, a campfire is going to give off heat to anybody who's around it. And those chemical hand warmers, you break those or crack them, then the chemicals inside will mix and give off the heat that you feel. All right, so there are 7 diatomic elements. two atoms. These diatomics are elements that exist bond to themselves in nature in order to gain a greater stability. Here they are, Hofbrinkel. That's how I remember it, Hofbrinkel, which is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Which means when hydrogen is by itself, it's going to want to be bonded to itself. If hydrogen wants to bond to something else, then we can break apart. But otherwise, it would like to be bonded together. So here we have a sample of one diatomic element. And here we have two different diatomic elements. So these are what we call particle diagrams. Sorry, it's messy. So you notice that the particles are taking up the whole space, which we're going to talk about phases in a minute. And that would indicate, you know, it would probably be a gas, a diatomic gas. So here we have our different phases. Note that the solid is clumped together. By the way, have you noticed that all of our particles are little circles? In a solid, they're clumped together at the bottom. So an example of a solid would be copper. Note that S means solid. In a liquid, they're a little bit more spaced out. Little more space in between molecules. Okay. In a gas, we're going to take apart, you know, fill up the whole container. Take up whole container. And we're going to talk more about this when we talk about phases of matter. Now, this last one is called aqueous. This is called, dissolved in water. So that's what this means. That means H2O. So in our picture here, we have H2O, the Mickey Mouses. O, H, H. So we got the Mickey Mouses throughout. And then you see we also have positives and negatives. So we're going to learn that a salt like NaCl is Na positive 1, chlorine is negative 1. So when you put them into water, it evenly distributes throughout and becomes homogeneous. So the difference between liquid over here and aqueous over here is that we have a mixture. Although it is indeed homogeneous, we have a mixture of something dissolved in water. And that's where we're going to stop. All right, if you have any questions, please reach out. Thank you.